So we also have regularization techniques like L1 and L2, and we also have learning rate optimizations. The learning rate is a crucial hyperparameter which influences the step size during weight updates. A learning rate that is too high can lead to divergence, while a rate that is too low may result in slow convergence. Techniques such as learning rate schedules or adaptive methods like ADAM optimization can be explored to enhance the model's training dynamics. In conclusion, the comprehensive redesign we have revisited and refined each aspect of the neural network configuration for time series prediction. The key to achieving optimal performance lies in systematic experimentation and analysis. So here, like we have implemented 100 neurons and 50 neurons for each layer, and also the batch size and the training and testing data split. And also these are all approximations which has to be trained and tested, which are not generalized or which are not mandatory to use this amount of training percentages and this amount of split percentages and this amount of epochs. So these are all training and tested based on your data set or based on the requirements which are given for the data set to be trained or tested. So by carefully tuning hyperparameters, exploring different architectural configurations, and integrating advanced components, we can develop a neural network that not only captures the intricate patterns within the time series data, but also generalizes well to unseen data in a more accurate and robust predictive model. Coming to the part 5, we are redesigning the neural network with 3 LSTM layers and 2 dropout layers. And here we are giving the testing percentage for the data as 30%, and we are training with 70% of the data. And the dropout rate is set to 20%. And we are going to continue with the same batch size, which is 32. And then here we are increasing the epochs for each LSTM layer to 60 instead of 50. So like I said, we are building the model with 70% of the training data. And here we are going to increase the layer configuration for the LSTM with 3 layers to capture the temporal dependencies. And it is also essential to assess whether deeper or shallower architectures may offer advantages. Here we are redesigning the network to see if by adding the one more LSTM layer and one more dropout layer, is there any tactical advantage for the model. So with this experimentation with various layer configurations such as 2 or 4 can help identify the optimal network depth for the specific characteristics of the dataset. And here we are increasing the neuron count to 60, and the dropout layers play a crucial role in preventing overfitting by randomly dropping a percentage of neurons during training. The initial design includes 2 dropout layers with a dropout rate of 20%. While dropout is a variable regularization technique, the optimal dropout rate may vary for different datasets. A comprehensive search for dropout rates ranging from 10 to 30% can be conducted to determine the rate that provides the best balance between overfitting prevention and model performance. And here we are choosing time series input sequence length. The choice of a time series input sequence length of 65 determines how far back in time the model looks when making predictions. This parameter should be adjusted based on temporal dynamics of the data. A sensitivity analysis involving different sequence lengths, such as 50, 75, 100, can help identify the optimal input length, which captures relevant historical information without introducing excessive computational complexity. With the help of the batch size, which is same as before, which is 32, the impact of the batch size on training dynamics and convergence should be carefully examined. So smaller batch sizes may promote better generalization, but they come at the cost of increased computational time. So these also have same learning rate optimizations. In conclusion, we have examined various aspects of the neural network configuration for time series prediction. The key to achieving optimal performance lies in a systematic exploration of hyperparameters, network architectures, and advanced components. Coming to the part 6 of the project, which is comparing network performance. So by doing a comparative analysis between two models, we can see neural network 2 is more complex than neural network 1 due to an additional LSTM layer and an increased number of neurons in each layer. Increased complexity can be advantageous for capturing intricate patterns, but may also lead to overfitting if not carefully tuned. Dropout layers. Both networks incorporate dropout layers for regularization, which is crucial for preventing overfitting during training. However, neural network 2 uses two dropout layers compared to one in neural network 1. Coming to the training epochs, neural network 2 is trained for a longer duration with 60 epochs compared to neural network 1, which is trained for 50 epochs. The, the additional epochs in neural network 2 may also increase the risk of overfitting if not monitored. In conclusion, the performance comparison between neural network 1 and neural network 2 is influenced by multiple factors. It is recommended to implement both neural networks on a consistent dataset to evaluate their performance on the testing set and potentially use additional validation sets of fine-tuned hyperparameters. Regular monitoring of training and testing loss curves along with performance metrics will provide insights into the model's learning dynamics and generalization capabilities. The adjustments may be necessary based on the empirical observations to achieve the optimal balance between underfitting and overfitting for each neural network. So, after conducting a thorough performance evaluation, the results suggest that neural network 2 demonstrate a slight improvement in predictive performance compared to neural network 1. The evaluation metrics utilized include accuracy, mean squared error, and the ability to generalize unseen data. So in this diagram, we have redesigned with the new LSTM layer and also a new dropout layer. If if these are not carefully managed, it may lead to overfitting of the data or training loss, which may result in time lag of the model's accuracy, or it may become tedious for the model to train based on the heavy batch sizes. So these batch sizes and these additional layers has to be considered very carefully. So coming to the conclusion, so in conclusion, we are going to do a model comparison, comparing the performance of the simple RNN and LSTM models, gaining insights into strength and weakness of each architecture. Hyperparameter tuning. Experimenting with hyperparameter tuning for both simple RNN and LSTM models includes the adjustments to learning rates, batch sizes, and sequence lengths. So as we bring this extensive project on the exploration and optimization of RNNs, we glean insights from the diverse components and phases that unfolded. Each segment of the project has added layers to our comprehension of the intricacies associated with harnessing neural networks. In summary, this project has provided us with a comprehensive grasp of the complexities inherent in the intersection of the time series data and neural networks.